So in this lecture I am going to discuss about Burger's equation and its numerical solution, and I think everyone knows that I am highly passionate about and interested in numerical method and numerical solution of fluid mechanics. So the idea for this lecture is just to give you a brief introduction about this mathematical model, the Burger's equation, and how we can solve this Burger's equation numerically. So I'm not going to discuss details about mathematical technique or like the fundamental aspects. Instead, I'm just going to show you a computer code using Fourier transform or first Fourier transform. So what we are going to do is we are going to take this Burger's equation and we want to solve this for x from 0 to L, and maybe we can choose a value of L, 1 or 2 or 4, whatever we want. And we are going to use the periodic boundary condition, meaning that we want to set the value of u, which is the dependent variable, the solution of Burger's equation. The value of u at x equal to 0 is the same as the value at x equal to L, and we are going to use an initial condition sinusoidal. Okay, so let's take a look at the computer code, which is very standard Python code. We have some input statement at the beginning, and what I'm going to do is I'm going to use the ODE int from SciPy integrate. And this ODE int, so we actually don't need to write the computer code for the solution, so we can just call the solver. So the purpose of this talk is just to give you the basic idea how we can use this numerical solver from Python, and similar solver can be used also from MATLAB and also from C++. Okay, so first we're going to do here in line between line 9 and 12 the temporal domain or time domain. So I'm going to take the maximum t for 1 and a number of time steps 100, and I have dt and t. So we first discretize the time domain and create a discrete time variable, and similarly we do it for the space. So for the space I have taken here from 0 to 1. So L is 1. I have taken 256 grid point, and then I have delta x, and then I have here the value of x or the x grid. So keep in mind I want to use periodic boundary condition. So one way technically to apply periodic boundary condition in MATLAB or Python is to discretize the grid in a way that the right boundary point should be removed from the grid. So instead of going from 0 to 1, I will go from 0 to L minus delta x, and this numpy routine arrange 0 comma L with a step of delta x starts from 0 and do not take the last point. So that's very easy way, simpler way to remove the grid. Or maybe we can use, let's say here, x equals linspace command. So linspace 0 to L, and maybe the number of points here I can say n plus 1, for example. So I will use one extra point, and then I will say x equals x square bracket colon minus 1. So I will remove the last point. So that then I started with a grid from 0 to L with n plus 1 points, and then I remove the last point, meaning that now I have n points, and also I will not have the last point. So different ways it can be done. The main point is straightforward periodic boundary condition is to remove the last point and then let the FFT routine do it internally. Then I have the wave number kx defined. Let's not discuss much about that. This is an FFT routine. We have to keep in mind, or another time I will come back and discuss about the manual or mathematical definition, how we can set it up, the wave number. Nevertheless, we need the wave number kx to apply the Fourier transform. And then I have here the initial condition u. So I denoted it by u0, which is sine 2 pi x divided by L. So this is just one sinusoidal wave. I have something here, so just forget that part. We can comment in this part, and then we can change the initial condition. So let's just forget that part. Okay. So the next point would be to solve Burger's equation. Is we are going to treat this as a system of ODE, meaning that we are discretizing the Burger's equation in space. So we are going to write the first derivative of my solution du dt equals something right hand side, and right hand side I'm going to call that RHS Burgers. Okay. So in order to write the Burger's equation in Fourier method, and to have the syntax with SciPy ODE int, we need to pass the first argument, my dependent variable, solution u. The second argument is the time variable, and then I have parameters. So in this case I have two parameters, which is kx and the viscosity nu. I have just called here kappa, my definition of kx, just to indicate that this is a local variable. It is immaterial what is the name here. It is important what I pass. Okay. So that the first line, line 33 here, I take the solution u, call numpy FFT routine, calculate first Fourier transform of u stored in u hat. Line 34, I take the Fourier transform u hat, multiply by the wave number and the complex unit, which is square root of minus 1. In numpy it is nicely stored as 1j. So this is my, on line 3, derivative in Fourier domain. So keep in mind that in Fourier method, derivative is straightforward. Differentiation becomes multiplication. So the first derivative of any function is I times the wave number times the Fourier transform. Then I calculate the second derivative on line 35. So this time what I do is for second derivative I multiply twice. So ik times ik is I square k square, or minus 1 k square. So I have programmed it in a way I don't need to multiply 1j twice or power. I can just write here minus with a negative sign and np dot power kappa 2 is square, and then multiply by Fourier transform u hat. Okay. So I have my first derivative on line 34 in Fourier domain, second derivative on line 35 in Fourier domain. Now I turn everything back to the real space. On line 36 and 37, I have inverse Fourier transform for first derivative d underscore u, and on line 37 inverse Fourier transform of second derivative, which is d2u. Okay, and then I have written here maybe du dt is du underscore dt, or I can just write du dt like that. The symbol, not sure which one is convenient. Keep in mind that in Fourier transform I have this right hand side of Burger's equation, which is negative u times du dx plus nu times d square u dx square. This will be a complex number in Fourier method. So I take the real part. Okay. So that's all. I have calculated the right hand side of my PDE, and from this example actually I can solve any 1D PDE. I can just calculate the right hand side. It's very straightforward. Okay, so now line 41 I call ODE int. So I say ODE int RHS burgers. I pass the right hand side of the burgers equation, and then I pass the initial condition, my solution at t equals 0, which is u0, and then I pass the time argument, and then I pass the parameters. Okay, so here the syntax for passing parameters is args equals a tuple. In Python you put just the parameters kx and new within a square bracket. Different way we can do that, but this is one simple way of looking at it. Okay, so that's all. So you have the right hand side, you program that and you call ODE int. You just need to know the syntax as written in line 41 and pass that right hand side, and then you get the solution. That's straightforward syntax. Let's look at the plot. Okay, so I just that's my personal choice. I take the solution u and then put it in a new variable sol and transpose it. It is not necessary. You can just deal with u as is. I transpose it, and then I create a figure to plot the solution. So first on line 47 I plot in space-time domain. I put in x-axis the time variable, y-axis the x variable. That's one way of looking at it. That's why I transpose it. Basically, maybe one common way of looking at it, we can put x in x direction and t in y direction. I have here t in x direction and x in y direction. So it doesn't matter. It is a personal choice. And then I have plotted using the p color mesh, and then I have also taken some sort of slice of the solution at t equals 0, which is the initial, and then I'm going up to all time step and then doing 10 at a time, up skipping like every 10th time step I'm going to plot that. Okay, let's take a look at it, the solution. So that should be very fast, and this curve here, the blue one, is the initial and the next 10 time step and next 10 time step and next 10 time step. Here I have not plotted written or denoted what is the x axis or y axis. In real presentation, actually it is important to have a proper axis label. So the x-axis here is time variable, y-axis here is space variable, and we can see the solution pattern here, how it changes. And here on the right side I can see a line plot. So this line here is t equals 0, and then I take another section here after 10 time step, and another section here after 10 time step, another section here after 10 times step. Okay, so I have 10 curves because I have 100 time steps. Okay, so now I'm going to explore a little bit of Burger's equation. So maybe I can see if I can bring the slide. That is the equation here. Put in the slideshow mode. Okay, so on the left hand side I have the time derivative and the advection term, and on the right hand side I have the diffusion term. So one property of the Burger's equation is that it is an advection diffusion equation. So the model, whatever the quantity represented by u, not necessarily it will be a fluid. It could be any species or any concentration. So it is a generic mathematical model, an interesting mathematical model. So viscosity nu, I can control that. So if I set viscosity nu equals 0, I can say that all terms are equivalent. Kind of I can say order of magnitude for the first term, order of magnitude for the second term, and order of magnitude for the last term, which is on the right hand side, will be the same if I set nu equals 0. If I set nu equals 0.1, then I will have a competition between the second term on the left hand side and the third term which is on the right hand side. So advection and diffusion. So diffusion will be 10 times smaller approximately or relatively. If I set nu to 10 to the power minus 2, then diffusion will be 100 times smaller. So let's say if I set nu equals 0, then this is a first order nonlinear PDE, and this is a hyperbolic equation. So it has a characteristic curve. It has a right moving wave. If the velocity or if the speed of the wave is positive, it will have a left moving wave if the speed is negative. Keep in mind that in the wave equation, which is second order, so I have a positive c and negative c, standard wave equation. So I have two pieces of equation, but here in Burger's equation I have one piece of equation, but it is a non-linear. So the speed here is u. If you can see here, my mouse is moving, cursor is moving, sorry. So if u is positive, then the wave will be moving to the right. If u is negative, wave will be moving to the left. And we can explore this here in the solution numerically. So maybe first take a look at what I have the solution currently with my choice of the parameter. So I have a sine curve, and you can see the next curve here is going to the right. On the left side it is going to the left, and on the left portion the curve is going to the right. On the right portion that the profile is moving to the left, but at the same time it is decaying because of the viscosity or viscous effect, okay, or diffusion effect. So let's say I have the viscosity here on line 16, 0.025. So I divide it by 2, which will be 0.0125. And now if I run the code, hopefully we run, yeah. You see that the solution profile has been changed. This time the advection is dominated by a factor of 2, so it is moving little sharper than it is diffusing. Maybe we can just go back and divide the viscous coefficient by 4. So we reduce this now by a factor of 4, and we can see that a sharp transition in the solution, meaning in Burger's equation we call this is a shock formation, is on the left portion of the solution has a positive amplitude, is moving to the right, and right portion of the solution has a negative amplitude, moving to the left, moving to the right, moving to the left. That is a shock. And at the same time it is diffusing or it is dissipating, so the amplitude decays, and at some point of the time in here 10th time step, 20th time step, 30th time step, and after 30th time step I can see that the diffusion term has been dominated over the advection term and the amplitude started decaying. Now let's go back and change this. Instead of factor of 4, let's say factor of 8. What happens? Okay, it is very similar, but let's do it by a factor of 12, which means I had originally 0.025. I am reducing it by more than 10 times, which is 12 times exactly. So I can see that some sort of oscillation. If I see if I can zoom this part in, so I can see that some oscillation has begun. If I go back and say this is 16 times, it might fail. So clearly I had some oscillation. So those are nonlinear instabilities. If I have diffusion too small, then I have right moving wave and left moving wave. They are strong, and there will be some sort of imbalance in the mechanism, and then the oscillation starts. Another way I can look at this, say I reduce viscosity by a factor of 8 instead of factor of 16, but increase the domain size from 1 to 2 and run the code. It should be similar to making the diffusion small, but this time I can see a slightly different behavior. So I can see 1, 2, 3, 4, 5, 6, 7, up to 70 time step. The diffusion term is dominant, and then the advection term is dominant, and the viscous term dominates at that point. It takes some longer time. So when I increase nu, actually this is in view of fluid mechanics, but if the Burger's equation represents Navier-Stokes equation, so increasing L domain size is equivalent to increasing the characteristic scale or increasing the Reynolds number. Okay. Also, decreasing the viscosity is equivalent to increasing the Reynolds number. So when the Reynolds number is large in fluid mechanics, we know that the advection term is dominant. We can now, the code will be slow. I have on line 18 256 grid points. So I multiply by this by 2. Remember, in the previous figure we have seen some sort of oscillation near the shock, and this time the code will be a little bit slow, but interestingly the oscillations are removed. Oscillations are removed. Let's zoom in here. So I still have some oscillation, but they are better. The stability has been improved if I increase the number of grid points. So let's say I increase the number of grid points in line 18, 256 times 4, which is 1024. This time the code will be a bit slow, but yeah. So we can see that if number of grid point increases, then this shock is captured much more accurately than a fewer grid points, and this times the oscillations are almost gone. And if I zoom in here, I see the oscillations are almost gone. So what does it mean here with this property is that if Reynolds number is large, then we need, or if the viscous coefficient is small, we need much more grid points in order to capture the shock development. If we want to remove the shock formation, then we have to add viscosity. We could also use some local viscosity here in order to remove the shock artificially, that's another option. That's one point. The other point is that this method that I have used is spectral method, so the derivative calculations are very accurate. Also, I have used ODE int, so that is kind of the higher order time integration. The Runge-Kutta type time integration is chosen internally, so that is something better. Maybe in another lecture I will demonstrate you, or maybe you can give it a try looking at Burger's equation, but just take finite difference method and Euler method, and you can see a huge difference. With the same parameter, the value of the viscosity, the value of the number of grid points, time step and time span that I have currently used, if you use the same parameters and use a finite difference method, Euler time integration scheme, you can see that this is really difficult to control the numerical instability.